Sorry I got cut off, but array in this case is, array is something that starts one place and then goes forever in only one direction. So while our line goes forever in two directions, the ray in this case might be CA, starting at C, going to A, and then we can put a line with one arrow above it to show that it's a ray. And then an angle, you guys are familiar with angles. There's actually more, if you believe me, there's more than one angle in this diagram. So I want to see first, before I write an angle, can you see more than one angle? So our eyes, and actually the symbol we use for angle, which is above the whiteboard in the classroom, the symbol for angle we use is this little angle symbol. So this angle symbol is what we put before the letters that create an angle, and it looks acute. So we might say to ourselves, well, ACB is surely the angle. But if you wanted, you could also say that this obtuse angle is an angle. So I can see an obtuse angle here, I can see an acute angle here, and whoa, if you're ready to blow your mind, technically this whole bottom part is also an angle. It's just a straight line. We call that a straight angle. So I am going to start with the most obvious angle here and just make sure everyone is familiar with how to write these letters. So when we write the three letters, when we write an angle by its three-letter name, I am going to draw the angle with the letters I use. So I'm going to call this angle ACB. Now, I do want you guys to also put the second option for this angle, which is if we go backwards, it is also acceptable. We can call this BCA. So angle ACB is the same as angle BCA, as long as we draw it. And when I say draw it, I mean the C has to be in the center because that's the vertex. This is called the vertex of the angle. So ACB or BCA are both talking about this angle here. And maybe I use this little marking to show you this angle. This is typical also of marking something. So if you have any questions, you can comment below, subscribe, like and subscribe, guys. And so on the next page, we have our getting started. And I know that you guys could read through this and it's very interesting stuff. So maybe I'll explain it if you're curious. It says, you may remember that when you were younger, you learned to estimate with counting numbers, and accuracy was not important. And then you learned to count and operate with whole numbers and fractions to determine more exact amounts. So exact is actually a real math word. There's a difference between, let's see, an exact number might be something like the square root of 2. This is maybe a little bit too much, but of course, if you wanted to approximate it, for accuracy, you can estimate the square root of 2. If you plug that into a calculator, you're going to get a decimal. It's like 1.7 or something. I literally can't remember. Because I usually like to use the exact, which is the square root of 2. We don't estimate anymore. So for example, you could determine that 2 times 5 plus 2 times 3 is the same as 2 times 3 plus 5. Oh my goodness, you guys. So this is actually distributive property, which is cool as heck. If you distribute this, you get this, and you can actually prove distributive property by showing that, what is 2 times 5? If you use PEMDAS for this one, 2 times 5 is in parentheses, that's 10. 2 times 3 is in parentheses, that's 6. And if you add them together, you get 16. In this case, we have parentheses here, so you do 3 plus 5 first, and 3 plus 5 is 8. And then you would multiply times 2. 2 times 8, also 16. Oh my gosh, isn't that so cool? That's the proof for distributive property. And so down here, it actually has written out distributive property, and maybe this is uncomfortable because you're used to seeing this first and this second, and they're just flip-flopped order. But this is still distributive property. Sorry that I'm writing this all out, but that's just your little example for now that we're mathematicians, we're going to show that numbers that feel whole and real, like when you're in elementary school, and then in middle school you learn about distributive property. Now we're actually going to work with things with like letters and showing that this will always be true. We can prove that this is always the case. So in geometry, creating and thinking about geometric objects is similar. There's a way to just sketch a figure, which is just an approximation. And there's also a way to draw geometric figures. These are two different things. When you draw a geometric figure, you're using tools like a ruler, a protractor, and a coordinate plane to make it exact and perfect. When you construct a geometric figure, this one is the coolest one. You can create exact figures without using those tools. So those geometric tools are called a compass, and then a straight edge, if you have one of those too. And a compass can draw something without measuring and making sure, for example, the square has all 4 congruent sides. You don't have to like measure them out. So anyway, it says down here, sketch and then draw each figure. So you will need a ruler for this one. I would love for you guys to grab a ruler in the room. Miss Awad should know that you have those, and you can share among your table. But for a square, for example, I'm gonna just sketch it. So my sketch might look something like this. Sketch. I mean, is that perfect? No. Do you all agree it's probably a square? Probably. If I tell you it's a square, it's a square. And then, using the tick marks would be the best way to do it. But after this, I am going to draw. So sketch, draw. I do not have a ruler on me right now. So I am going to use, the best thing that I have, I guess, which would be a piece of paper with a determined length. Ugh, I don't know. Like, I could just do this length and that length. And of course I'd need to make sure there's 90-degree angles too, but please try drawing this with a ruler. Isosceles triangle, you're gonna do the same thing. I'm gonna give you guys a second to do this on your own. Isosceles triangle, the definition is in the room, up on my triangle poster that's rainbow above to the left of the Promethean. Isosceles triangle means 2 are the same length. I'm gonna say those look pretty much the same length. So here is my sketch. And then I would use a ruler to make sure that those were exactly the same length. So maybe I would have exactly 2 inches, 2 inches, or centimeters. Okay, leaving you time to do that. Pause the video, etc. So when you are ready for number 3, they want you to construct a circle, which is, I don't have a compass with me, but if you could find someone in the room who knows how to use a compass, there are a few. One of them in the room has just like a circle. It's like a little flat tool, and you literally just stick your pencil in it and go in a circle, and it's that will work. But I also want to make sure, even if you don't construct it perfectly with a compass, I would like to make sure you guys know these vocabulary words. So I am going to list out all the vocab here for you. So after you construct a circle, and there's a lot of space for this, so maybe you try construction up here and then you go down here. I'm gonna make sure you guys all know these vocabulary words. So if you have a circle, and in geometry, we can label the circle and call it by the letter of the center point. So if I wanted to tell you, hey, here's a circle, I'm gonna call it circle M. There's no reason I use the letter M. Actually, often you're going to see the letter O to represent a circle, but let's just say I'm going to call this is circle M. Now, circle M may have a radius after the center. So the center of the circle, it says here, the definition, a segment from the center to the outside is called a radius. So I am just going to draw any of these would be considered a radius. And then in order to write I guess I should have said this is circle M. And in order to write and notate this particular radius, I need another letter for this. So I'm just going to come up with letter N. So this is radius, and that radius I'm calling MN. And I put a line on top of it to show that it's a line. There are an infinite number of radii. So for fun, I guess I could write down, this is the plural of the word radius. It's radii, and there are many radii, one single radius. And these are used for a lot of formulas. So if you've heard of pi r squared is the area, anything about pi, the radius is used. And if the entire thing all the way across the two radii, I'm going to call this S. MS is another radius. The entire thing, maybe you guys have already remember this, is called the diameter. So diameter, I can call this SN or NS. It doesn't matter. Either direction works as long as I use the end points. And so these are things hopefully you've seen before. Now, there is also something called a chord. You aren't really going to work with chords until Math 2, but if you have any other line across the circle that does not go through the center, so literally just like from here to here. I don't know how long that is. It's not helpful, but this is what a chord is. So I'm going to come up with two new letters for this. Let's call them P and Q. This is called a chord. And you can use that word for any, what is this called? Connecting line between 2 points on the circle. So I went out of order a little bit over here, but we've touched on chord, diameter, central angle, and inscribed angle are next. So we're going to create angles out of some of these. A central angle is an angle whose vertex is at the center of the circle. So I'm going to remind you that the vertex is like that corner any point, and an inscribed angle is an angle whose vertex is just on the circle, typically inside the circle. So here is, I'm going to make a central angle here, and this central angle, I love central angles. They seem the best because they are like slices of pie, slices of cake. They make a perfect little sector of the circle. M, N, L. I'm going to say that this is a central angle. So for central inscribed angles, we're going to use the angle symbol. So that one's this little guy. So this central angle LMN, I'm going to call this angle LMN. So if you read this, if I just said, hey, student, go to blank, 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 that means this central angle here, which has a measure if you used a protractor. Now, this measurement is the measurement of like the slice of pie. We're going to call an inscribed angle an angle that's just on the outside of the circle. So maybe like this angle. So this angle has nothing to do with the center of the circle. It's over here on the side. It's just inscribed within the arc of the circle. I have used so many letters already, I cannot keep track of them, and I don't want to use R because R is right here. How about G? This I would call angle GPQ, and this is inscribed, and it's called inscribed because it's inscribed in the center of this, or around the inside. I'm so sorry, I should not have said center. Inscribed around the inside of the circle. Inscribed angle GPQ. Okay, almost finished. We now have the word a secant. So secant can be confusing. I could skip this one, but the secant is just like a chord. And the difference between a chord and a secant is the same difference between a line segment and a line. So let me remind you, the difference between a line segment, a chord is like a line segment, and a secant What's the difference between a line segment and a line? Well, a secant continues past those endpoints. So if I came to this circle and I pretended I was I don't know, something in space, and I sliced through it, like if this line went on forever, if a line crosses through bang once, crosses through bang twice, we call this a secant line. And secants are found in other parts of math, especially in calculus. So you might not see them again later, but a secant line, this would be line PQ, and I will make sure it has forever arrows so you can tell. But a secant is very, very similar to a chord, except the chord is confined between those 2 points. And finally, the arc of a circle is any unbroken part of the circumference. So hopefully you know that circumference is the fancy word for perimeter. I'm going to write this up here. So circumference, this is the circle word for perimeter. There is a root here, like circumnavigate the world, circumcise, truly, circumspect. There's a lot of words that have this, and so this just means circle. So it's just the fancy word for the perimeter of a circle. And so any of these outside arcs count when we just ask for an arc. It's like the crust of the pizza. So I could say this is a small arc, arc LN, and we denote an arc, make sure you have this down, with an arced line above it. So this is how we call arc LN. You don't need to write any of these English words. When we're talking in geometry, we just need symbols and letters. But if we're saying arc LN, this would be a minor arc here. If you wanted to also talk about the arc from L all the way around the circle to S, you could say arc LS. And this is just for fun, but students, is there a difference between this arc LS and this arc LS? Because technically there's a way to go from here to here, the short way and the long way. And the answer is, if you specifically mean the long way, you can use one of these points in the center to say, I'm going from L to S, but I'm passing through G. LGS is that arc. So if you wanted to write the 3-letter name LGS, this helps specify that you mean the arc goes the long way. We call this arc a major arc when it's long like that, but that's another Math 2 skill. So this is where I'd like you to get today if possible, and then I'm going to make a new video for the rest.